Welcome back to the next episode of the AI Ascend podcast. In this episode, we're going to be talking with Jinedra and Ramtin, who are two of the authors of a recent AI research paper titled Matmole or No Matmole in the Era of One-Bit LLMs. Welcome to the podcast.
Thank you very much. Excited to be here.
Awesome. So in this podcast, we will start by talking with Jinedra about his experiences pursuing a PhD and coming onto the project. Then we'll go over some of the more technical questions with Ramtin about the paper. So first of all, for Jinedra, what university are you attending and what degree are you pursuing or have you completed?
So I am at the University of South Carolina and I'm pursuing PhD as of now with Dr. Ramtin Zand. He's my PhD advisor. And my research areas as of now are quantization and large language models and working with whatever comes as of now. Yeah.
Great, that makes sense. And how long have you been doing AI research?
So AI research, I would say that I I have been started reading about AI since last year, and during last semester, I really delved into more specific things like transformers, quantization, and architecture, etc. That really came along when I took classes with Dr. Zen. He teaches a class here which is called Edge and Neuromorphic Computing class, where he goes over all this stuff. So that's when I really got interested in doing this research.
Great, great. And what inspired you to pursue research in large language models and optimization techniques like quantization?
So it started off as a project, the course that I was talking about with Dr. Zan. It was Edge and Neuromorphic Computing project. I took up a project. I went to him and I said, like, okay, do you think if we could deploy a large language model on mobile devices, do you think it's really a project worthy of a thing? And he said, like, definitely it is. And most of the things we are working on in our lab is work on those things. He had work on a paper which he had implemented BERT models on TPU architecture. So he was interested in that. And that's where when I got started with doing LLM research. And during that time, I found out that, okay, if I have to deploy a large language model, I have to do some tricks like quantization. And that's when I started learning about quantization.
Cool. Yep, that makes sense. Yeah, quantization is a really exciting field. Um, Cool. So, as a new PhD student, what was it like stepping into this project, especially given that it was already in progress when you started?
Yes, I'm very thankful of the previous researchers that already had started this project and whatever they have been working on, and I'm still learning from them. So uh, initially, I think it started off as a implementation of scale sim simulator. It just gives you how many uh, compute cycles you can get of learning some architecture like large language models uh, in something like a, a systolic array architecture like TPUs per se. So at that time, then I scale it up for working with all of the language models that we have discussed in the paper for OPT models and GPT models and Llama models. And that's where I started. That's from where I started the project, and that's where I built it up from.
Cool. And what were the biggest challenges you faced when contributing to this research, and how did you overcome them?
So the biggest difficulties I would say is keeping up with the literature and whatever is being going on in the community right now. So every day there was new papers on transformers, new quantization techniques, everything that is being constantly updated myself. At the same time, I also have to keep up with my knowledge that my knowledge is concrete, and I have to be completely sure of what I think a particular thing is. So during that time, I used to, during the start of the project, when Dr. Zan and I discussed this project, we had landed very lengthy discussions of like for, let's say, sometimes an hour and a half, going back and forth, discussing the project. Okay, this is what I think this should work as. And he used to think like, okay, maybe you are missing something there. This is what you're missing. So To overcome those things, I used to code and get back to him. Okay, Dr. Zand, this is how I coded. This is working perfectly fine. Do you think the same? This is how it is working. I was implementing it from scratch, and he was like, okay, it looks good, but maybe you're missing something here. For example, when I was implementing transformers, I couldn't. I hadn't implemented a phase of the transformer or the KV cache, and that was changing my understanding a lot. Versus his understanding was a lot better than me. So this is what I overcome by going back and forth with Dr. Zan and working with him in this project.
Great, great. Yeah, so spending a lot of time going back and forth and understanding the intricacies of the LLMs.
Yep.
Cool. So what specific aspects of this research paper were you most involved in? And how do you feel like your contributions shaped the final outcomes?
So after we discuss our project, my contributions were okay. He had some ideas about uh, designing the experiments of the project that we had discussed, but my inputs were like, okay, if if it really depends on something like context length, we should figure out, okay, we should run experiments for different context length. That would, I would say, like one of my contributions. And then after we run experiments, after making sure that okay, we are running everything, and I have to be completely transparent if I want to make this work for everyone. So maintaining a very good GitHub was something of my contribution, and everything, bringing transparency to whatever we are working on was something of my contribution. And then on later stages, when we were coming up with figures, Dr. Zan had a different idea. He's saying like, okay, bar charts are a better option. Then I was saying like, okay, I think I have drawn something better. Let me show it to you. And I think the heat maps particularly gives you the whole idea of, okay, this particular architecture with this context length has this much amount of uh, percentages of improvements in this side, in the projection layers. So that was something of my contribution that came out really nice, I would say. And then when we were discussing the conclusion of the project, uh, we were really uh, we are really struggling with, okay, how we want to finish the paper. And Dr. Zan has some idea. I think we were discussing it, but it wasn't coming in context to everything what we are discussing on. Then I said like, okay, Dr. Zan, you had discussed this thing before. Why don't we end the paper with something like Amdahl's law? Some At that time I didn't call it Amdahl's law, but that's a similar line of thought that we are going through. Amdahl's law was his idea. So that's when we thought like, okay, this would be a really smart way to end the paper with one graph that would show up uh, all the possibilities of language models. If you work with small language models, how much of a speed up you will get, medium size versus large size. So those were my contributions, I would say, with this project that really I think is uh, came along great.
Cool. Yeah. Yeah, and then that discussion of Ahmad's law ended up being important in the introduction of the paper as well, correct?
Yes, yes.
Great. So, great. So, how has working on this project influenced your perspective on the field of AI and your future research interests?
So what I see right now is, okay, people in the community and in research areas, they are really going forward all in with GPUs, and they are going all in, increasing the context length to, let's say, thousands of tokens now. We see that context length of large language models nowadays is 512,000 tokens, and it's still growing. This really increases the demand of GPUs, and it is computationally very, very expensive. So going on, I think whatever I'm working on, bringing efficiency to with different architectures and not just GPUs on the same side, thinking about something which can be implemented efficiently. Let's say attentions for, say, if we come up with a better hardware, better architecture to implement that, or if we cannot come with a better hardware, can we implement something other than attention in a hardware like Mamba per se? So moving forward, these are my thoughts on the AI. research feels that we should not go all in just one direction, bringing heavier and heavier GPUs and working with them. And the big tech companies surely does not think that way, and they are going all in with whatever resources they can have. So this is my take on it.
Yeah, for sure. Okay, yeah. So discussions about the architectures and these new hardwares that we can use.
Yes.
Yeah.
Yeah, that's part of our next paper also, that we have discussed a new architecture that could use partial improvements from the attention side as well as the projection side. Uh, we haven't named it yet, but this is something that maybe Dr. Zand will discuss in the when he's talking about this. But we have another paper that takes on from this paper and how to implement it more efficiently. If there's an architecture that could speed up what speed ups we have talked about in this paper.
Cool. Cool. That's exciting.
Yep.
And looking ahead, what are you most excited to work on or learn about during the rest of your PhD journey?
I think I had some other discussions like previous work that he had work on. There was a paper on approximations. He was working on approximating rather than quantizing, and this is rather a new take for me and something new to learn that I'm really looking forward to. I don't know about the whole PhD journey as of now, but something new that I want to work on next semester, maybe this. And I would say going more on the hardware side, something like a PIM-based architecture, which is called processing in memory, which solves a lot of problems by not moving the data around and just doing the processing in the analog domain. Yeah, those are the things I'm excited to learn about more as my PhD journey continues.
Cool. How does it work to do some hardware, to do research with hardware, such as looking at the pin-based architecture in academia?
So I think everyone does start from doing some kind of simulation, running experiments on them, and then devising the architecture which would suit whatever results they have got on. Let's say if they are working with pin-based architecture, they are working with crossbars, and how big of a crossbar they need, what things they have to take care of, and they have been they different components to it. I'm new to this field, so they have different components to it, like ADC converter, DAC converter. You have to work a lot of things in order to fabricate with when you're working with these hardwares.
I see. Excellent. Yeah, that sounds pretty exciting.
Thank you.
Awesome. Cool. So moving on, now we will start discussing the research paper with Ramtin. And so the first question is, how have the strategies for quantization changed as we dropped from 8-bit quantizations of the weights down to 1-bit? What are the major paradigm shifts in your perspective that got us this far?
Yeah, interesting. Well, I mean, we should say that the idea of 1-bit LLMs is coming from a paper that was published earlier this year. It's called BitNet, and maybe there was another paper before that too, in late 2023, in which they investigated this extreme quantization in parts of the language models. Now, this has been done by Microsoft Research. Fundamentally, the work like this has been done before. So like there are papers that if you go back, for example, to the context of convolutional neural networks, you can see that we have a paper called Binary Connect that has, extreme quantization in different layers of deep convolutional neural network that we're working with. So I wouldn't say things have changed, or we actually had a paradigm change going to the extreme quantization from what we had a few years ago, maybe back in 2017, 2018, the convolutional neural networks. The thing that has changed is the scale of these large language models. So we're talking about billions, tens of billions, hundreds of billions of parameters. And I've been giving a talk last week at Zurich, and we talked about sustainability of large language models. And there is an interesting work that goes back to 2021 that talks about how much accelerator or GPU time you need to train these kind of networks. And we're talking about hundreds of years of accelerator time. Now, a back of the envelope calculation tells us that you probably need to have thousands of these GPUs to be able to do a kind of research, this kind of research. You quantize a part of that, you do the training from scratch. So not everyone can do this kind of research. So it's less of a paradigm shift and more of a having access to that fleet of GPUs that you can put together to do this kind of exploration that we have been doing in other types of models, for example, convolutional neural networks, and bringing them to large language model. And from my point of view, that's what Microsoft Research and the team that worked on that project did when they could go for extreme quantization of LLMs. It's less of a paradigm shift and more of a having access to resources to do this kind of research. Yeah. For large language models, yes.
Yeah, sounds like it was a practical decision because if you quantize it, now you're using less resources, less GPU, VRAM, less compute.
Yes. Ideally, that's the direction we can go. But there are nuances here and there too that we can talk about.
Great.
Yeah.
And can you explain the differences between the two main categories of transformer quantization, the weight only versus the weight and activation quantization?
Sure. Yeah, so this is fundamentally deep neural networks, and transformers is one of them. They involve different layers, and these layers mostly involve some kind of matrix vector multiplication, matrix multiplication, and so on. So weights we're familiar with are trainable parameters, and we call them weights. And a good strategy is quantizing them. That's going to reduce the memory footprint, and we know that's weight-only quantization. And it has been known that we can quantize weights while maintaining accuracy to 8 bits, depending on what kind of workload you're working with. Now we also have activation, which means every time that we use this matrix multiplication, we're getting these results, we're generating new results, which we call activations. Sometimes these activations actually go to an activation function and experience a nonlinear transformation. Sometimes they don't. Sometimes there are some linear transformation following each other. So in the context of large language model, we know that there is some sensitivity to the representation of the activations. So we know that we can go lower bits, we can have lower bits for weights, but it's not the same thing for activation. It can get challenging, especially for activations that we have in the attention heads. And there has been a lot of research showing that there's a limitation of that. You can technically quantize the activations too, but you lose important information through this kind of rounding mechanism that we're doing in simple words that can reduce the accuracy. But if we don't actually quantize the activations, not only we're not improving a big portion of the model in terms of the memory usage, but also computationally would be different. Because if you're working with floating point activation, even if you quantize the weights, your matrix multiplications are still floating point. And that can have major implications. So the biggest difference is that typically we are more sensitive to quantizing the activation because we need that information. And weights can be approximated through quantization. And ideally, we don't lose that much accuracy overall.
Okay, I see. So essentially, when we quantized the weights, that was an easier step to take because we didn't lose as much performance by quantizing the weights. But then when we started looking at these other methods of quantizing, such as quantizing the activations, now suddenly we're facing more sensitivity where if we reduce it, then we lose out on some performance a lot more.
Exactly, yes. And it is more pronounced in transformers than CNNs, I would say.
I see. So how did BitNet contribute to the rise of the era of one-bit LLMs?
Well, I think BitNet was the era of one-bit LLM. So even the chose this title of Era of 1-bit LLMs in the original paper. Again, it goes back to a few months ago with the work that Microsoft Research has done. It was a little bit confusing, I should say, because it's not all 1-bit, and that's exactly where we come to the picture. So when it started, I could see that the community is getting very excited about this idea of extreme quantization. And then we thought early stages, we had some discussions with some of my graduate students at the time, and we could see that everything is not 1-bit actually. Some parts of the model is 1-bit. And this is exactly what our paper was about. We were like, okay, if we can provide a roadmap that how much of this computation is actually improved by 1-bit quantization, then we can have a meaningful pass forward in the era of 1-bit LLMs. So we can't just begin the era of 1-bit LLMs, get super excited about it, and then get into wrong choices of research potentially. So we wanted to create that kind of roadmap very early on, immediately after this paper was out, to kind of give an idea to the research community, ideally, to say that, okay, you know what, it's exciting, but let's just sit back and think about what we should do next and where it makes sense to focus on. Because it's definitely an exciting era. It's definitely an exciting name, the era of 1-bit LLMs, but we also want to be cognizant that even at this stage of this research, it's not fully 1-bit, so we have to have a clear roadmap how we can move forward, and that's what we're hoping this paper that I worked on can provide to the audience.
Okay. Yeah, great. That was a interesting answer. So how did you come up with this idea to explore the impact of partial enhancements on 1-bit LLMs on their overall performance?
That's a great question. Yeah, I mean, so I as Jinendra mentioned, I teach a couple of courses in our university. And one of those courses is computer architecture. So I do machine learning research a lot, but a different part of my research is focused on computer architecture and bringing them together. So there's an old law which is very practical, and I really like that law. Even when I teach it in the class, I'm like, this is very useful in real work. And actually, I'm teaching it tomorrow in my class. It's called Amdahl's law, and bringing that mindset of computer architecture to LLMs could be useful. Now, what is Amdahl's law? Amdahl's is very simple. It came out for when we were doing parallel processors were coming out, and the idea was if we improve only a part of a system, that was just computer architecture, how much total improvement we can get in the system, right? So we thought that immediately after seeing 1-bit LLMs and the early models of 1-bit LLMs, we noticed that not every part of this model is binarized or ternarized. And the first thing that came to my mind was, well, this is a classic case of Amdahl's law. Before getting super excited about where we can go with it, we have to go a little bit deeper and see, are we improving only 2% of the system, or we're improving 98% of the system? And that was because I could see that our community, our machine learning community, is very fast growing community. Like everyone wants to have everything ready in a month. Then in 2-3 months moving forward, in a year moving forward, we can start directions that are not meaningful, and then that creates a branch of misguided goals. So we immediately thought, okay, if we bring that computer architecture mindset, Amdahl's law mindset, to the 1-bit LLMs and do a thorough analysis, then moving forward, we can immediately have correct choices of goals for the next steps and where we're going to go with that. That was the whole idea, having a kind of a roadmap for the entire community that is very excited about this new era and avoiding fundamentally misguided choices of goals for moving forward. So that was when this whole thing began.
Great. Yeah. The community is definitely moving really quickly.
Yeah.
So what did you discover about how the impact of 1-bit LLMs varies significantly with the size of the language model and the context length?
Yeah, absolutely. Yes, so that's something that we explored heavily in our work. So we had like a bunch of different models with different sizes and also different context length. As Ginu mentioned, Jinendra goes by Ginu. So if I call him Ginu, that's why I call him Ginu. I'm used to calling him Ginu. So what Ginu mentioned was, so at the time I was only thinking about the model sizes, and Ginu brought up this great point that, well, context length can be very important too in this research, and that's what we did. So we do have heat maps in the paper that we show different model sizes and we show different context length. And the whole point was you can categorize these models in simple terms, tiny models and very small models and large models. And then we have small, short context lengths and pretty long context length that we experimented with. What we learned was, in many cases, that we have smaller language models, but very large context length. Most of the computation actually happens where we don't have any improvement through 1-bit LLMs. So that was the whole point that we wanted to see. We wanted to see where these 1-bit LLMs are the way they are now, they're the way they're today, because they're not making everything extremely quantized and only parts of it is extremely quantized. We wanted to see where it makes sense. Now, after doing this experiment, we learned that if we want to work with less than 1 billion models, which is small language models, most of your computation happens in attention heads. But a lot of practical models that we're using today are they have tens of billions of parameters, if not hundreds of billions. And what we noticed that the larger the model gets, more of the computation is actually improved by 1-bit LLM paradigm, because they improve the projection layer and most of the computation happens in the projection layers. So that was great because we could see where it makes sense to use this kind of paradigm, this 1-bit idea. And there are actually applications that it doesn't make sense to focus too much on them. Because we shouldn't forget something, 1-bit LLM is an interesting idea and it can provide some benefit for us. But if you don't have a custom hardware built for it, you might not get the benefit that you expect to get. So the idea here is that should we jump and start building a new computer architecture for this kind of model, or we should just sit back and try to focus on the parts that this, new 1-bit LLM architecture is not improving. And that was the debate in the community a little bit too at earlier stages. There were works that were focusing on attention heads, but we were thinking, okay, so if you're improving the attention head, and it makes sense because that's the part that 1-bit LLM is not improving, but how much of the computation is really happening in that part? Is it worth focusing on that part, or is it worth building hardware for 1-bit LLM? So what we learned was, in simple words, to summarize, in simple words, if you have large models, the vast majority of your computation happens on projection layers and not attention heads. And 1-bit LLMs actually improve the projection layers. So maybe it's not worth focusing too much on improving whatever is left. If 99.99% of your computation happens on the part that we're already improving, we might not want to spend too much time and effort and money on improving 0.01% of the system. But if you're working with smaller language models, you're probably not going to get as much as benefit that you want to get with 1-bit LLMs, and then you're going to have to have some innovations on that attention heads as well.
I see. Great. So how might the advancements in hardware accelerators influence the practicality and adoption of 1-bit LLMs in real-world applications?
Yeah. Well, I think Gino mentioned, talked about it a little bit. We have been working on the hardware development, the accelerated development for 1-bit LLMs to early stages, doing some kind of high-level architecture level analysis to see what benefits we can get based on the paper that we're talking about. So there's a follow-up work coming out real soon. It's under review right now, but probably soon it's going to be on archive, which we investigate the possibility of using new kind of architectures for this kind of models that we're talking about. And the particular architecture that we have developed and we have designed so far uses what Gino mentioned, processing and memory technology, along with systolic arrays, which are typically used in TPUs. So we are making a hybrid architecture that combines the TPUs with a new type of architecture called processing and memory. So doing that, what we learned was, as we expect to get 2-3 orders of magnitude improvement, the maximum improvement we can get by using 1-bit LLMs. But the problem was, Gene and someone else in my lab, Massa, they started working on the research, and they used the BitNet CPP models, and they deployed it on a Raspberry Pi. Gene, you can correct me if I'm wrong, but you could get roughly 10 to 20 tokens per second using this kind of technology. Is that correct?
Yes. The smallest model was giving us 20 tokens per second, and the largest model was, I think, 6 tokens per second. So
yeah, sure. So we're talking about 6 to 20 tokens per second, and this is far from 1,000 times improvement, right? So it's promising, but what we learned was, if you get a model and deploy it on an architecture that's not designed for that model necessarily, you go from this big promise of 1,000 times, 10,000 times improvement to 2 times improvement, because the architecture is not designed for that kind of model. And when we use our architecture that is specifically designed for 1-bit LLMs, we couldn't obviously get 1,000 times improvement because there are always overheads, but we could push it to 50, 60, 70 times improvement in throughput by using a custom hardware. So the answer to your question is, I think after the 1-bit LLM paper that we put out, Matmul or no Matmul in the era of 1-bit LLMs, this actually provided a roadmap for us to build an architecture, and we went after the part that we thought that is the most important part. Now at the end of this new paper that soon is going to be out, we show that now if we show the breakdown, now you can see that again it's going back to the most majority of the computation is happening on the parts that are not improved by 1-bit LLM. So before, that part was contributing to less than 1% of the computation. Now, after building a custom hardware, the part that we didn't care about, now is contributing to 60-70% of the computation, because we have extremely improved the other components. So now would be the time to have innovations for the attention heads that are not improvement, for example, by 1-bit LLM paradigms. I think the architecture is extremely important. I mean, to summarize again, like I said, I think it's not only it's important, but also we do have some preliminary results in our lab that shows that you can achieve significant improvement that cannot easily achieve by just getting these models and running it on existing hardware that we have for machine learning models.
Great. That's very interesting to hear about how now that you've made these hardware optimizations, that's now the ratio of each side significantly changed.
Mhm.
And now that opens the door to new optimizations in this other area as well.
100%, exactly, yes.
Great. So what advice would you give to practitioners and researchers who are implementing extreme quantization in their LLMs?
Yeah, I mean, this could be like summarizing the points that I just said. Like, there are a few items that we should really pay attention to if it's a startup working on this particular kind of application. I mean, one motivation that we started working on this kind of project was because we have a project funded by NSF Career Program earlier this year on real-time sound language translation. We have another collaboration with a startup that works. We are integrating LLM with social robotics to teach middle school and high school students metacognitive skills. That was why we started working on LLMs, because we did have particular applications. Now, let's say you have a startup that you want to work on this kind of applications. The first thing you have to pay attention is that there's not a one solution for all. Like, we see 1-bit LLMs, we get excited about it, it's very promising, but it might not be the thing for your application. Depends on the context length of your application, depends on the model sizes that you can have in your system. If you have a tiny hardware, you can have hundreds of billions of parameters on your system. So then it makes sense to go back, hopefully look at our paper and look at the heat maps that we provide and say, okay, my applications falls into this category, and then that would be the potential solution for us. So it's very application dependent still. There's not, the first thing I want to say is that there's no one solution that works for everyone perfectly. Now, the other point can be the hardware. We should not underestimate the effect of hardware. We just talked about it. The example I provided, which is actually based on the project that we're working on, social robotics with Gino and NASA in my lab. So we're talking about 10, 20 tokens per second, while we thought we're going to get thousands of tokens per second if we use one with LLMs, right? That was because we don't have a hardware for that. We shouldn't underestimate. It's great to be very excited about algorithmic innovations, but it's a full system. Software, hardware, code design, algorithm, hardware, code design. That's extremely important in this field that we're working on. Now, maybe the last thing I want to say is that we should look at the end-to-end system always for practical applications. Working on LLMs is super exciting. We are doing it, but again, I go back to the social robotics example that Gino is working on. It's not just one bit LLM. It's not just LLMs alone in that system. We're having a conversation with a robot. There's a part that is doing voice recognition. There's a part that LLM is converting a text to text. Then text should be converted to voice. Probably we should do some actions in our humanoid robot that we're working on. So this whole thing, when we say, all right, I want to have a conversation with a social robot, and I'm hoping that the robot can understand 5 words per second, and it can generate 5 words per second, because then it can have a seamless conversation similar to what we are doing now. That's great, but if you hit the 5 words per second just on your LLM, you're forgetting that no, you probably need to generate 20, 30 words per second, because there are other components in your end-to-end system that are time-consuming too. You have to wait for them to do the job. You have to look at the breakdown of your system and see how much of your system is on the LLM side, and always make sure that you design the system for the worst case. Overall, I think these are the 3 things: application dependent, hardware is important, look at your end-to-end system. This is, if I want to provide an advice to a startup or to new research lab working on the field, I would say pay attention to these 3 things.
Wow. Yep. That makes sense. Very exciting. So yeah, application dependent, the hardware components, and end-to-end.
Yes.
Perfect. All right. That was all my questions. It was really exciting to have you guys on. This is a really exciting research paper, and I'm really looking forward to seeing what you come out with in the future and what comes out in this world of the LLMs.
Thank you so much for inviting us. This was very exciting, and thank you for the great questions you asked.
Thank you, Luke, for inviting us again. It was really nice having a good conversation with you about this.